Well, hello and welcome back to Electrical Fundamentals Engineering 201, and we're going to be working on experiment number 6. So this is the last experiment or the last lab for this term. So the civil engineers are probably pretty excited about that. I believe they just take one term of this. The mechanicals and electricals will be with us for another term or two. So this lab that we're working on is a lab where we're learning to use a tool, that being the oscilloscope, to make measurements. And that's an important tool. That's going to be our go-to tool for the next couple terms, making measurements and whatnot. So I want to go through this. It's not necessarily a lab where we're going to try and prove or disprove some electrical phenomena or something like that, but mainly just getting practice using a tool. Although we'll see if we can learn a few things along the way. So with that, let me change views here and see if we can. There we go. So like I mentioned, we've got, and I'm going to zoom in a little bit, but I'm panned out here to give a kind of a more broad global view of this thing. I've got a circuit right here. This is our circuit that we see in the laboratory, and we'll talk more about that. And then I've got the oscilloscope here. This is our measurement tool, and really this just allows us to measure in this direction, the vertical direction, voltage, and it allows us to measure on the horizontal direction, time. That's really all that is. But it's got a lot of bells and whistles and things like that. And I will try and give you some help on this. This is one where it's really neat if you can actually touch the knobs and the dials and whatnot. For the civil engineers, I think this lab will suffice, and that you've been exposed to an oscilloscope, that you can kind of get a sense of what it does. For the mechanicals and the electricals that may want more exposure to this, I'm going to send a couple of websites along on the email that I've introduced this video with. And on those websites, I will give you some other options if you want to try and pursue some of this on your own. There's some tools out there. You can use your sound card in your computer to kind of make an oscilloscope, or they have some little boards that you can buy fairly inexpensively. So if you want to pursue this and want to do some more oscilloscope work, I'll give you some leads on that. The reason we don't send everyone home with an oscilloscope is this one. This is a, well, for lack of a better term, Chinese knockoff of a Tektronix scope. It's a good scope. I actually bought one personally for myself. Bought quite a few for the school. It's Handtech. If you look at the font up there on that, it even looks like the Tektronix font. So they knocked off clear to the graphics and whatnot. But this is about a $200 to $300 item right here. So a lot of people probably wouldn't want to put that out for a class. I could understand why, and then you still need a function generator and things like that. Now, if we were to go with a Tektronix tool, and we've got some great Tektronix scopes in the lab, you're just going to move the decimal point over one spot. So it's going to be about $2,000 to $3,000. So that's why we're doing this in video form. So let me, while we're panned out here, grab the camera here. Try not to make anyone seasick, and show you a couple things. So over on the this has been the designer, the electrical tool that I've been using all term long, and over in one corner of it here, we've got a function generator. Okay, and you can see I can set the frequency here with the rough setting. So we're going to be using 1K and 10K today. I can adjust the frequency with the fine setting right there. I can change the amplitude, and I can also change the waveform. Okay, so sinusoidal, triangular wave, square wave, and whatnot. So that's going to be my function generator. It's not a great function generator, but it's built in, all in one. It's like many things, when they try and do too many things, they don't do any of them well. But this is going to suffice for us just fine today. So that comes over, I come out of the function generator. I come over and I have my circuit, and the circuit is very basic there. I've got, come on, focus. is a capacitor. This green thing, or this thing right there, is the capacitor, and we'll talk a little more about those, and then the resistor. And that's it. We don't even really care, as long as the resistor value is roughly in the range. We're good with that, and likewise the capacitor. It's not about that, although labs in the future will be when I meet with you next term. So that's that. Let me put the camera back here before I make people sick, and then bring it down and zoom in to the oscilloscope. I think that'll probably work. Move this over a little bit. Yeah, I think we should be good here. Okay. So there's our oscilloscope. I'm going to go ahead and, well, maybe before I turn things on, let me talk about the lab itself now that we can see this a little better. And you're going to have this in hard copy form. So if it's a little hard to see here, but basically this is our circuit. We've got a capacitor and we've got a resistor, and we're measuring with channel 1 the voltage essentially across the resistor. We're measuring with channel 2 the voltage across both of them. So we'll consider channel 2 as our input voltage, and then maybe channel 1, the voltage across the resistor, is the output voltage. And then before we're done, we'll switch the location of the resistor and the capacitor. And we're going to do this. The capacitor is 0.1 microfarad, 1 times 10 to the minus 6 farads, and the resistor is 1 k ohm. And like I said, the exact value of those is really not that important. As long as we're in the ballpark, we should be good with this. We're going to be running at 12 volts peak to peak. So from the very top of one to the very bottom of the other, that's going to be 12 volts. And we'll spend a lot more time next term talking about how to measure that, because if we were to measure this with your digital voltmeter that you're used to, it wouldn't appear anything like that. So peak to peak RMS value, we'll spend a lot of time in the future next term. Don't worry about it this term, but next term dealing with those and trying to relate those. The last thing is we're going to run this at a frequency of 1,000 hertz and also 10,000 hertz. So that's what we've got going with that. I'm not going to tackle the questions right now. We'll go and grab the data, and then we'll talk about answering those questions, and I'll try and give you some help with those. Before we fire things up, I might talk a little bit about capacitors. Maybe I'll put this down here so we have a surface. Lots of different types of capacitors here, and you not only need to size them by the value, but you need to have so 10 microfarads or 0.1 microfarad or picofarads or nanofarads, but you also need to have a voltage rating to make sure that the you don't exceed the voltage rating. And then the last thing is oftentimes they have a ring or a notch on it. This one, in fact, has a little indentation here, and it's also got a plus symbol, so we would take this as the plus terminal. Depending on how they're made, they may or may not be what we call polarized, have a positive terminal. This one doesn't. This one here, again, is, you can see that indentation right there, so that, again, would be the positive side. This one has an indentation again, you can see that. So this would be the positive side, and there's a little arrow saying that that's the negative side. And what do we have here? Oh, this one has a indentation on both sides. So it's like this one here. It's non-polarized, so indentation on both sides. So if you wonder what that indentation is, why there's an arrow pointing to the negative, why there's some plus symbols, yeah, these can be, depending on how they're made, a polarized device. So that's probably all we need to know right now about capacitors. Let's go ahead and get started with this. So I'm going to turn my function generator on, and I'm going to turn my oscilloscope on. And there we go. Okay, so as promised, this is measuring voltage in this direction, and it's measuring time in that direction. Okay, and I went and got your data beforehand so I could have it printed out and be able to talk about it. So it's pretty well set up, but you know, I could cut the video short and say, there you go, but let's not do that. Let's go to auto setting, get the computer to auto set this thing. That's usually usually get a pretty good chance of getting things messed up. So, okay, so if I just come up to this thing and maybe ask the computer to do its thing, I get a couple waves that are like that, okay? And these are the channels, the blue, this one right here. As we go through this, I recognize some people have trouble with colors. I'll refer to it as blue, but also try and give other designations. So we've got the blue one right there. We've got the yellow one right there. The blue is channel 2. The yellow is channel 1. Okay. So what they're measuring is from these probes. Okay, so I've got channel 1 right here, and I've got channel 2 right here. Move this camera over a little bit. Okay, so channel 1 right here, channel 2 right here, and I can grab the probe off the circuit. You can see that I unhooked it, so I must have unhooked channel 2. And the way the probe is, this is what the probe looks like. A lot of times in lab, students would somehow get the end popped off and they'd panic that they broke it. And oh my gosh, I'm not going to be able to pass the class now, I broke something. No, these are made to do that. The end comes off and you can then hook this in different ways and whatnot. For our purpose, we'll just use that end. And you can see there's a little hook on this. You can actually hook onto something. See, can you see that? Anyway, so there's a little hook there. And then the other thing on this is it has a lead that goes to ground. And that's something to think about when you're measuring a circuit, particularly if you're trying to use this on measuring some live AC. You have to be really careful. Is your circuit ground the same as this oscilloscope reference? If it is not, you may not want to hook up this ground wire. We're not going to have to worry about that in the upcoming labs, but if you start to do a lot of oscilloscope work, that's something that you may want to think about. The really cheap and dirty trick is to not ground your oscilloscope, but that has some safety problems and whatnot. So anyway, so that's what we have. We have the one lead here, and essentially another lead here, ground. Sometimes the scopes don't have this and they'll have a dedicated ground over on the scope, but ours does. The probes can get out of adjustment, and when you go into a lab, you always want to keep the probes with the scope because they've been calibrated. There's a little calibration thing over here where the scope has an internal function generator. We can hook our probe up there, we can look at it, and you can put a small little screwdriver. There's a hole in the bottom of the probe here where you can adjust it with a screwdriver and make sure that it's zeroed. So I've done that. I've taken care of that. The last thing is sometimes probes will have a little switch on them for a magnification factor, a 1x probe or a 10x probe, and then that's also accounted for inside the machine. So just be aware of that. Once in a while, a machine won't take that into account. So if it seems like you're always off by a factor of 10, that may be what's going on, but we're in good shape on this one. So I'm going to put this probe back. You should see that line go back and behave a little more. Okay, so we're back to both our waves there. So when you walk up to an oscilloscope, and this is just a measurement tool, if for instance I change this, oops. So come on, here we go. There we go. So you can see that yellow wave, I'm changing the amplitude of it pretty significantly with this. Now that's not physically changing the circuit, that's just changing the magnification. That's that's like looking at a map with a magnifying glass. Okay, it doesn't change the difference between two cities, it just changes your view of it. Now if I go over and on the board, if I go and adjust the amplitude, then I'm really changing it. But really, I can't get any trouble messing around with these knobs because I'm not changing the circuit itself. I'm only changing how I am looking at it. So when we walk up to these things, we always have a couple channels. Sometimes scopes have multiple channels, many channels. We'll use some 4-channel scopes next term. But this always controls my my magnification in the vertical. Just pause that there. This knob controls my magnification in the vertical and where it's located. And most scopes are laid out like this. This knob controls my magnification on channel 2 in the vertical and where it's located. And then this knob controls the how it's spread out on the horizontal time-wise. So let's go ahead and look at this. I'll see if I can. Yeah, I think I like that. So I'm going to look at the menu for channel 1. One thing that we oftentimes want to do is get these down and compare them together. So I want to move them down, and I can move them, but I have to be careful. I want to get them referenced to the same thing. So one thing that I can do is I can ground this. So channel 1 should be grounded, and then I can move that down. And if I ground both of them and move them like that, I will be able to reference them the same. This is kind of nice. You can just press this button and it automatically finds ground. Okay. Then I will do the same for channel 2. Go to channel 2 menu and I will ground that one. Okay. Now we're starting to get somewhere. And a lot of times students will say, and that, let me get back here. So a lot of times when we have something like this, students will, in lab, they'll come up to me and they'll say, "Oh, my nothing's working. I think the function generator is broke, and it looks like it's putting out a DC signal." Well, they're just really zoomed in. So you got something like that. Likewise, you can be so zoomed out. Sometimes we'll do that because it's really nice to see where those cross when that's vertical, but don't fool yourself into thinking that you're looking at some vertical function. Okay, so play around with this until you get what you're looking for. Now, the one thing that I need to really be careful with, and I always document, and when I did this, I just took pictures of this. This actually has the feature where you can capture the waveform. It just comes out in an Excel file or data point. So I just took pictures of it. I thought that was probably easier. But we see here this little number right there, and these numbers are probably the most important numbers because that's our legend. Okay, if you look at a map, the first thing you might do if you have to walk from one spot to another is you want to see the legend. How far is that in miles? Okay, 1 inch. So what? Well, how many miles is an inch? Just like here, these divisions. So what? Each one of these divisions from, get a pencil here, although I'm not supposed to touch the screen with a pencil, but going from, let's say, that point right there to that point right there, that's a division. How much is that? Well, we know it's 80 microseconds, 10 to the minus 6 seconds because of this. And if I change this knob, I change that scale. So if you sketch these curves, make sure that you put down what that factor is. Likewise here I am, and sometimes we do this because one wave will be much, much smaller than the other one. But just on face value, if you didn't know this, you would think those were about the same. Well, they're not the same at all because one is 1 volt per division, the other is 2 volts per division. So if I get this now they're both 2 volts per division, so I can compare them on face value. And again, if you have a very small signal, sometimes you will have these set differently, but you need to be careful and be aware of that. Okay, well, we could spend a lot of time talking about triggering. We've got all kinds of different menu options here, and I kind of really like analog scopes for the simplicity of it, but these digital scopes is obviously the way things are going. Students like these because they're used to the menu structure, and you can do a lot of cool things with them. If you want to take these two waves, you get the math menu here, and you can subtract the two channels, okay? Or you can, what are we doing there? Is dividing by the channels. So there we go. We've got the two channels. Okay, so get that back. You've got a horizontal menu, all kinds of different menus, and the younger generation of students really kind of likes the way this is laid out, because this is the way other devices that they've used work and whatnot. That's fine. But in the end, we're making measurements, and we've got cursor tools here that we can use to measure things. If you want to, there's the time, so you can measure horizontally with the cursors. There's voltage you can measure. But in the end, we really are just measuring based on these divisions here, okay, on our scale factor. In the horizontal, it's time. In the vertical, it is voltage. Okay, so that's what's going on with this. So the civil engineers that are finishing up this class and probably glad for that and going on, the oscilloscope is a great measurement tool, and it allows you to measure things in real time. Time on the horizontal, voltage on the vertical, and it's a little more sophisticated than that. You can start to do plotting on here and whatnot, but about 99% of the measurements you're going to do, time on the horizontal, voltage on the vertical. That's for the mechanicals and the electricals next term. That's what we're going to be doing almost all of the time, and we'll get some more practice with this. We'll set up circuits and go through this, and usually all of my knob twisting over here is going to be getting these things so I can compare them properly on an equal basis, getting them grounded at the same point, and getting the scales such that I know what's going on. Okay. For the electricals, spring term, hopefully we're back, you know, I hate to say this on video, but hopefully we're back together face-to-face spring term, and they can finally get some hands-on with these. So anyway, if you're frustrated about not getting hands-on, we've had lots of students go through, and it used to be we had labs where we had 3 people per station. Now we just have 2 people per station. But you know, when we had 3 people per station, sometimes you didn't get a lot of time to touch and handle the equipment. And those people have gone through and are pursuing great careers in engineering. So if you feel like, oh, I just think I need to touch that oscilloscope so I can be a successful engineer, all I can give you is sympathy, but I think you will probably succeed whether you're able to touch the oscilloscope or not. So anyway, just a word there. Well, so we could go through and get our data, change the position of the resistor and the capacitor, change the frequency. I'm going to change the frequency knob here, so we've got it like that. There we go. So we got a lot higher frequency. There's higher frequency yet. Okay, then we go back to lower frequency, and that's actually changing the what the signal is doing on the function generator. So we could do all of those things and make those measurements. I have already done that. So what I'm going to do now is change and look at that data. So I'm going to cut to another screen here. I think this is the one I want to go to. Yeah. Okay. So this is actually the data, and you're gonna hear some rustling around here because I'm going to try and relocate things. Okay. So what we've got here, this is, like I said, the data that you're going to be getting. I'll email this to you. You probably will have already seen this if you opened it before you watched the video. So here is, we essentially do 4 circuits. Here's 1,000 hertz. with the capacitor there and the resistor there, and this is our data. And I was careful to make sure that I got your legends there, and also so we know which channel is which. The yellow, and if you print this out in black and white or have trouble with colors, the yellow or the smaller one is channel 1, the blue or the larger one is channel 2. Then we go and we switch. The only thing different here is we've switched the position of the resistor and the capacitor. Right here, the capacitor was up top, resistor was down here. We've switched those positions. Same frequency, different curve. Then we go to 1,000 hertz. Okay, and I guess to put this in perspective, excuse me, we go to 10,000. I'm sorry, 10,000. But put this in perspective. Go back here to 1,000. The electricity that probably your lights are running with now, if you're in the U.S., which most of you are, I assume, is 60 cycles or 60 hertz. Okay, 60 hertz. So this is turning on and off. This is oscillating a lot faster than even the AC plug-ins and lights that you might be familiar with. So then, like I said, we go to 10,000. Okay, and the go back to the capacitor being up top there, and we get some data. And it's interesting to note that the performance of the circuit changes. Remember, the resistor is not a frequency dependent device. The resistance is the resistance no matter what the frequency is, but the capacitance changes the frequency omega, and remember omega is 2 pi f, so that as the f changes from 1,000 to 10,000, the impedance of that capacitor changes, and it effectively changes the circuit. So that's why this graph looks a lot different than this graph. Okay. And then finally we change the location of the resistor and the capacitor, and we're still at then 10,000, and we've got something like that. And we might you might say, well, this would be a good time to use our adjustment knobs and change the magnification so we can get that yellow wave up a little higher. I made the judgment call that it was worthwhile to keep the legends the same. If you were running the show here, you might make another judgment call, and it might be a better judgment call. But this is getting kind of small. Any smaller, and I definitely should have changed that. So that's the data. I'll send it to you just like this, so you'll see it in color and whatnot. Let's figure out what you're going to do with this data. So I will switch back to this screen here, and let's see, I'll turn this off. Okay, so your questions. Some of you are probably just wondering, what questions do I have to answer so I can get done with this lab? Fair enough. Okay, and again, you've got this in PDF form, so if it's a little bit hard to see, you've got it there. So assume the input is the reference voltage. Determine the ratio of the amplitude of the output over the input and the algebraic difference between the phase angle for the input and the output. Okay, we're going to be doing this a lot next term. These two measurements, measuring voltage and measuring phase shift, those are going to be huge next term. So it's just getting you into the practice of that. Okay, let's look at doing that. So I've got the data here. I just printed it out. It's not in color, but I think we'll be okay. And see what we've got here. Maybe I'll grab a notepad. Okay, so this is the first piece of data. There's those 4 cases, and this is the first one. And you can, I'll go through this on the first one, and you can do it for the other cases. So with this one, what I wanted to do is I wanted to find out what this phase shift was here. Okay, so the phase shift is from there to there. The phase shift is from there to there. Sometimes people think that the phase shift is from here to here. Well, that's not true, because this one is increasing and that one's decreasing, so that's not the same point. Here I have this one that's increasing, this one that's increasing, so this is the phase shift. Right in there is the phase shift. Okay. So what I need to do is I need to figure out how many degrees that phase shift is. Well, what I can do is I can look at one of these waves. Let's say this wave right here, this one. Okay, I could look at either one, doesn't matter, but I'm going to look at that one. And I'm going to measure the essentially the time it takes to go from there to there. Okay, and I'm just going to count divisions because I know a division is 80 microseconds by this legend. So there's 1 division, 2 division, 3 division, 4 division, 5 division, 6 divisions roughly. Okay. So roughly 6 divisions. So what I have done is I say that 6 divisions is 180 degrees, because I know that one complete cycle of this wave from here clear over to here is 360. I just kind of shortcut it because I didn't want to have to count that many. I mean, it's a little bit like taking your pulse. You count for 15 seconds and multiply by 4, right? Okay, same thing here. I just counted for half of it, and then I know that that is not 360, but is rather 180 degrees. So now I have to figure out this phase shift. How many divisions is it? Well, there is 1 division, 2 division. You could say, well, I think that's a little more. That's fine. You can take it as a little more, a fraction. Normally when we're in lab, students just sketch these out, and you get pretty good data just sketching them out. Okay, so I know my phase shift is 2 divisions. I know that 6 divisions is 180 degrees. So with these two facts here, by ratio and proportion, okay, that theta is 2 divisions and 180 degrees is 6 divisions, I can get theta is 60 degrees. Okay, so that's my phase shift, 60 degrees. Now, while we're playing around with the time, let's consider something else. You're not asked to do this, but let's look at the frequency of this. We know that 180 degrees, that's half of a period, right? I mean, you could measure from there and take the whole period, but we'll just say that's half of a period. So that being half of a period, I can say that 6, that's the number of divisions, times my legend, 80 microseconds, 80 times 10 to the minus 6, and then I multiply that by 2 because this was just half of it. So there's the 2 because I was only looking at half, the 6 divisions, and the legend, 80 microseconds. So this turns out to be 0.001 second. And the frequency, of course, is equal to 1 divided by the period. So I come up, I flip that, and there's obviously, I must have more numbers on here because it didn't come out nice and round. You can do that in your calculator. Comes out at 1,041 hertz. Well, that's pretty close. Okay, close enough for us. But that's how you can make time measurements on this. So we can measure horizontally in terms of degrees like we did here with the phase shift, and we can also measure in terms of time. If you wanted the phase shift in terms of time, you could do that too. That's fine. But I really want the phase shift in terms of the angle. Okay. Now, all of this work and talking about hertz, we don't want to forget that most of the time when we're doing our analysis, our calculations, our book work, we're talking about omega in radians per second, and radians per second is 2 pi times the frequency f in hertz. So always remember that. It's fine to work in hertz, but if you have to compare that to radians per second, remember they differ by 2 pi. So that's how to get the phase shift, and you can do that for all of these cases. Okay, this is still 1,000 hertz. If you move to 10,000, it's a little bit harder, but that looks roughly like about a half division, and we're 8 microseconds. Okay, so that probably gets you about where you want to go. So let's look at the voltages. So we wanted to try and figure out what was our input and our output voltage. So I have down here, I have the channel 1. That's the smaller output signal, I'm going to assume. And I have channel 2, that's the larger blue input signal. So if you're looking at this in the file on the computer, color monitor, this will be, the blue will be the larger input signal. the yellow will be the smaller output signal. Okay, so if I look at then the larger input signal, that's this one. Okay, it should be 12 volts peak to peak. If I go from, that's the lower peak and that's the upper peak, so if I count 1, 2, whoops, do this again here, sorry. If I go from this lower one right here to this upper one here, I want to find that vertical distance. So there's 1, there's 2, 3, 4, 5, 6. So I've got 6 divisions there. What's my scale? Well, 2 volts per division. 6 times 2 is 12. 12 volts peak to peak. So it should not surprise me that my input value, the amplitude, which would just be from here, because that's the 0 point, up to here, I have 1, 2, 3 divisions. So 3 divisions times 2 volts per division gives me 6 volts. Now the smaller one, the output, that's this one right here. Okay, let's look at that. What do I have? How many divisions? 1 division, 2 division, 2.5 divisions. So 2.5 divisions times 2 volts per division gives me 5 volts. So that would be 10 volts peak to peak. Well, we want to come up with the ratio of that, the output to the input. So it'd be 5 volts divided by 6 volts is 0.83. Okay, so you can go back and do that on this first one. You can do it on this one. It's going to be a little bit harder when you go to the higher frequencies, but I think that you're up to it. You can do that one, and you can do that one. Those are way different there, aren't they? Okay, so that is how you tackle this first question. Okay, so determine the ratio of the amplitude of the output over the input. That's what we just did. And the algebraic difference between the phase angle for the output and the input. So you're going to have that ratio, and you're going to have that theta difference for all 4 cases. Okay, so you'll do that for all 4 of those cases, all 4 of those pictures, all 4 of those data points that I send to you. Okay, and the last question, this is a great question to end lab with, is a great question to kind of wrap up the term with, is, and I said we weren't going to be trying to prove any phenomena, but this is just too good to pass up. So it says, from the laboratory data that you have gathered, can you support Kirchhoff's voltage law? Show your evidence and conclusion below. And the hint, this is a huge hint. Think of this visually, not numerically. Okay, so we're going to see if we can do Kirchhoff's law. So what I'm going to do is I'm going to look at this graph, and I'm going to look at, this is the input. This larger one is the input signal, right? And I'm going to pick a point that I can reference on this. So I'm going to pick when it crosses, when it is increasing and when it crosses. Okay, and I'm going to go and I'm going to look at the other signal, which is negative about 1 1/3 or 1 1/4 divisions, right? So take 1 1/3, 1 1/4, multiply by 2, you have that negative voltage. That's what that is. Okay? And then I'm going to go look at just the same frequency, but when we switch those two. So that should be this one. Same frequency, but when we switch these two, and I'm going to look at the input where it's 0 and increasing, and I'm going to go up here and see what value this is, and that takes on a value of what? About 1 1/4 or 1/3 divisions. So if you take this, that is negative 1 1/4 or 1 1/3 divisions, multiply that by 2, and you take this, that's positive 1 1/4 or 1 1/3 divisions, multiply that by 2, and you add them together, what do you get? Well, you get 0, don't you? And that's what this was. And I picked that 0 point just because it was an easy point. You could, if you wanted to, you could pick a maximum point, and sometimes it's harder to find the minimums and the maximums than it is to find where they cross. But let's do this. Let's take this point here. We'll say that that's the maximum point. And what do we have this other wave? We have a positive 1 division, so that's going to be 2 volts, right? We'll come back over here. Same frequency, same point here. What do we have there? 2 divisions, 4 volts. So if I take the 4 volts here, and I take the 2 volts here, what is 2 and 4? 6. I get that point there, don't I? So indeed, I mean, the answer is yeah, Kirchhoff's law works. There was no stipulation that Kirchhoff's law only worked for DC. It works for AC, it works for DC. And you can actually show that. But the big thing is you have to show it for a consistent time. And time, for instance, when you look at these waves here, if you just say that over here on the left-hand side, that is not probably the same time as over here. Okay, so what I do is I find the same time by referencing it to a known point on one of the waves. I take this one as the input, and I say I'm going to always look at the same time on that one. And Kirchhoff's law will work. So when we did this face-to-face, I usually had to go over this a couple times, and then I would even take the sketches that students would make, and I would show them on their own sketch. So if you have to rewind this a few times to get this, don't feel too bad. And I'll go through this again very quickly. What we do is, for the two circuits, this one is 1,000 hertz, and you can do this on 10,000 too, and I'm going to ask you to do that, but you need to make sure that you use the thousands when you're comparing the thousands and the 10,000s when you're comparing the 10,000s. But there's the 1,000 there, there's the 1,000 there. So what we do is we've got this input, we look at where it's 0 and increasing, and the other wave is at a negative about 1 1/4 divisions. Then we go to this one. This input one, again, it's at 0 and increasing. And this other wave is now at about positive 1 1/4. Okay, well, negative 1 1/4 times 2 plus 1 1/4 times 2 gives you 0. So what that is saying is that the voltage across our resistor plus the voltage across our capacitor is equal to the input voltage, because this one right here, this is the voltage across our capacitor, because this is channel 2, which is measuring the voltage across your capacitor. This one is the voltage across our resistor, because this is channel 2, that's measuring the voltage across the resistor. So when I add this wave here to that wave there, I am getting the total across this thing. Okay, and they do add up. So the key there is you have to add them at the same time. Obviously this AC is changing with respect to time, so if you're not adding them up at the same time, it's going to appear that Kirchhoff's law does not work. But if you do add them at the same time, Kirchhoff's law will work. So that's really what I'm wanting you to do on this. So you're going to go through these measurements here and spend some time and with those graphs and prove that one to yourself, and write it up and turn it in, and you should be good to go. So I will leave you with that. If you have some questions, shoot me an email. I'm happy to try and answer that. And that's a good way to wrap up our laboratory, wrap up experiment 6, and wrap up essentially the term, I guess, except for the final. So I will talk to you soon. Thank you for watching. Take care.